and thank you for having me here. And today I'm going to talk about interactive images and videos and 3D. Since we are talking about interactions, I also want our our talk to be interactive as possible. So feel free to interrupt, whenever you are in person or on Zoom, if you have any questions, all right? And I want this to be a sort of roundtable, seminar talk. All right. So to begin with, I want to show just a corner of my study. As you can see from here, it's not my study room. It's shared with me and my daughter, right? So there's a pink ball and there's a blue piggy bank. Those are my daughter's precious possessions. And there is a vision science textbook. That is a really good book, by the way. And that is me. That is mine. So as you can see that although it's a good book, I haven't read it for a while. So my daughter put her piggy bank on top of that. And I just wonder, this is just a very normal and regular everyday pictures, right? I'm just wondering some very simple questions, right? What will happen if I just poke the piggy bank? This is a very simple question. I don't even need to bother to ask you guys. So ideally, right, as we can see, if we give a force to this piggy bank, depends on how heavy it is. It will roll or it will slide. It might hit the pink ball, and then the pink ball might fall on the ground and it bounces a little bit, right? And this is what we already have in our common sense knowledge because of our understanding of the physics in the world, right? And I just want to still double check whether it is the case. So I really poke the piggy bank a little bit, and here is here is what happens, right? And I tried different times, as we can see. In total, at the night, it's a boring night. I tried 50 times of this same experiment, and I get very diverse results of different videos. Depends on slightly different on how heavy the piggy bank is, and also how hard I'm able to push that, and what are the directions, and so on. So as we can see, the final goal of our group, this is just one example, but our final goal is we want to bridge the reality and the digital world. If you think about every image and every video, it just captures one specific point in our space and time, right? At this location, at this moment, I'm going to capture the moment of the real world. And that is a screenshot of the real world. But we know that through this picture, there is the underlying interactive physical world behind that. So a very natural question for us is, just given that captured moment, can we understand the world? And then can we actually be able to generate all kinds of counterfactual futures of that? And essentially, we are interested in answering the so-called what-if questions. What will the scene look like if we take certain actions on it, right? Poking is just one specific user interaction. You can imagine anything that you can do in the real world. I want that to happen just as realistic as possible, right?
Why do you call it what if and not just a world model?
Sorry, what? Yeah.
Why don't you call it a world model?
I will touch that later. So there are different buzzwords. World model is one of the buzzwords. And in computer graphics, people use digital twins and so on. Yeah. So yes, this is world model essentially. So
well, can you share screen?
Oops. Oh, sorry.
Thank you.
Apologize. I thought I already shared the screen. Okay, can you see the screen now?
Yes, thank you.
Okay, great. All right, just for the sake of online audience, I just want to show, this is the scene that I just depicted 1 minute ago. I apologize about that. All right, so next, let's talk about why do we care about that? Essentially, creating interactive images and videos across different counterfactual scenarios will benefit in many ways. What if our beloved family can stand in front of us from 1,000 miles away and say hi to us? Or, what does, Sydney Harbor look like if in future, like the sea level rises for 5 meters or something? Or what if there is a giant obstacles that block the road and we want to see how our self-driving vehicles will react? Or what will be looking like, or what will be the climate consequences if we want to build a new highway in our city, right? So the paradigm is actually largely driven by, how sort of like people have, basically my research is basically largely inspired by, people have such a recreative mind, right? In cognitive science, right, people call it recreative imagination or something like that. Essentially, that just like what Costa said, we have sort of like a mental world model. By seeing this image, if we take a picture of this image and we just imagine, what if it's like snowing? What if there are a lot of people? What if the thing gets flooded? Or what if I actually see a sunny day, but I imagine what happens in the dark night? Or what if it happens in a different climate situation and so on? So we are able to simply imagine and create visual pictures in our mind. And this capacity is called recreating mind. So our goal is trying to have computers to be equipped with a similar capacity. All right. So as I mentioned, there are two cultures. One is just called world models. That is coming from sort of a broader machine learning field, and it can be dated back to actually 1970s, and it got popular from Julius Schmidt-Huber roughly a few years back. And this paradigm actually models the dynamics directly from the sensor observations. Essentially, it will learn a mapping that trying to take the past visual observations or sensory observations as an input and also a user action as an input. And then it will directly predict the future observations as a consequence of this action, right? Usually this mapping is parameterized by a deep neural network and will learn from a lot of like action and observation pairs. And it's heavily data driven. That means it basically like ignores the existing human knowledge about the world. It just learns those knowledge from data. It directly generates observations rather than generate a state. And it has advantages. So you can see here. So 3 years ago, I can't really imagine that we are able to create such a realistic video footage that just coming from generative diffusion models. But now it's all possible. That being said, it's not really hard to actually stress test our generative model and find out quite a few different cases that is not physically informed, because everything just learned from data. And on the other side, as we can see, it's like a sort of model-based, world models. So they also have an interesting buzzword now. It's called digital twins, right? So essentially, we want to encode all our knowledge, like physical knowledge about the world, into a formal language, like math equations and eventually code. And then we run the simulations by having access to the full state of the world, and then take actions and run those simulations and generate another state. If we have a renderer that we are able to convert that state into a sensory observation, that is what we see here in this video. As we can see here, everything follows some of the rules that we encoded into these computer programs. That means we are directly get our existing knowledge encoded into our predictive program. That being said, it also has limitations because it can hardly be directly connected into our real world observations, because real world observation is usually just a partial observation of the world. Running simulation usually assume that we have the full state. So there is a gap between like this digital world and the real world. So if we think about like the desired things for interactive images and videos, firstly, we need them to be photorealistic, and also we need them to be physically plausible. And since we are generating a video, we also hope that it can be temporal coherent and it can be highly controllable, because we want our resulting video reflect precisely about different user actions. And in the last, we want them to be used for everyone. So it's not only just domain experts, everyone can be potentially used it. And this is a quite ambitious goal, but I'd like to argue that now is the right time to work on this problem, because it's with all the tools nowadays that we have, I think this problem is approachable. But in the meantime, we haven't yet solved that. So it's a perfect research question for us to investigate. So why do I say that is, there are a lot of great opportunities. In the past 3 years or past few years, we have witnessed so much progresses in different domains like 3D perception, simulation, and the generative models, right? So if we think about 5 years ago, right, I can't imagine that we have a segmentation network that can basically segment anything in an open vocabulary. But now we have the SAM2, right? And if we are able to we also can reason geometry much better from just a very sparse set of images. One example is Duster. And we are able to have some basic physical understanding, which I'm going to show later. So the perception models have advanced so much. It helps us to understand our world better. But so far, we haven't really very closely linked them to be able to build an interactive world yet. And simulation has also advanced a lot. If we think about 5 years ago, there is no really easy to use simulators like Tai-Chi or NVIDIA Warp that enable us to do different dynamic simulations. And different fields, of course, different domains, they also build their own knowledge-based model. And nowadays, they also trying to modernize them and writing some code to actually depict their models in different toolkits. And lastly, generative model like diffusion models that are able to create super photorealistic video footages nowadays. It shows as a promising tools actually to replace physical-based renderings, which is quite amazing, but arguably it still lacks a lot of physical groundings. So there are great opportunities here, there are great challenges, and now I'm going to show throughout my talk, I'm going to show the key idea here that my group has been establishing towards solving this problem. That is trying to mimic basically the mental world model of humans. Instead of directly generate a condition, directly formulate this as a conditional video generation problem, we want to take images as input and then create a scene model that encodes semantics, geometry, appearance, and importantly, physics. And then we will use existing physical simulators, or we will basically build new simulators that are trying to update our scene that reflects the full state change within our scene model. And then we'll basically leverage either generative modeling or physics-based rendering to create realistic video footage and then compose that with our existing observations. So we call it a perceive and simulate and render. Hopefully in the next, you can see that almost all the works I gave basically just follow the big paradigm here. I would like to stop here a little bit if you have any questions. So far, so clear?
As opposed to basically conditional video generation, where you're constantly creating many different futures that have different uncertainties.
Yeah.
You're using an actual physical model.
Yes.
That removes that uncertainty and has just one future.
Actually, it's interesting that those physical model, you can also model uncertainties. Because most of the physics model we defined in a closed set, those are the parameters we are able to run. But in the real world, there are also some of the uncertain parameters. So simulation can be actually modeled together with some uncertainty, but yeah, your understanding is correct. Yeah. Any other questions? Yes.
Yeah, since you're also trying to estimate physical properties and do like some society, if you're only observing, your only observations are like a sequence of images.
Yes.
How can you realistically back out like things like mass or friction that require like actual forces or impulses? That you don't have access to.
Yeah.
Is that where the uncertainty comes from?
Yes, exactly. That is an excellent question. So if we only just observe a passive image or video, as in many situations, we have to have some uncertainty in this physics, right? If I have a bottle of water, this one is not a good example because it's transparent. If I just have a bottle of water, I don't know how many water inside, right? So then there is uncertainty about basically ranging from its mass should basically have an interval. And that is also something that we'll do when we do this type of physical simulation. So uncertainty partially coming from uncertainty about our physical understanding. But as we can see, it's still an extremely hard problem in order to establish the full scene model from partial observations. So uncertainty also coming from uncertain part of its geometry or its composition or some other part. right? If we only take one image, on the back of the back of the shape is never going to be seen, right? When we want to roll the object, right, there will be uncertainty related with the unknown geometry on the back. That's also basically weighing those type of uncertainty. Any other questions? All right, great. Next, all right, let's coming back to the problem about poking this image. All right, so let's see what we can do. So firstly, we want to try, how about just generative video to image to video models? My student really tried prompt engineering a lot, and they found basically a very detailed, I'm not going into the details, but he provided a very, very detailed instruction about how to prompt that in order to generate better images. That being said, here is what we got from the latest open source model roughly like 1 year ago. And this field has also advanced a lot. This does not reflect the SOTA results. But as we can see, right, most of the videos are still photorealistic, but the dynamics are just not there, and it does not really reflect what we see in the prompt. And we also try, this is the latest greatest model by August 2024, which is roughly half a year ago. We also tried the latest closed source model at that time. It's called Clean AI, and here is what we get. It has full imaginations and it makes this piggy bank to be very, lovely tools, lovely toys, but it just does not reflect the real world physics. We're not getting a real world footage where instead we are getting a cool animations. Right, here is another example, very simple ones, just a bunch of domains. Right, so here is the results. A clean AI learns that it might actually trying to follow some of physics and then fall down, but it fall down in a very weird way. Right. So here is what we are able to get with physics informed generation. Now let's discuss about the details. The details is just following the 3 different paradigms: the perceive, simulate, and render. Given one image and also user control. Firstly, we want to get perception. Perception is not only about reasoning, semantics, but also reasoning about different things like a geometry. Like we really want to estimate the surface normal of that, because later on when the object changes its position, we need to reshade or relight that object. Right. So this is why we care about normal albedo. But we also want to get instant segmentation to be able to figure out which object is dynamic and which one is actually fixed, and what are the obstacles, and so on and so forth. Next, we talk a little bit about physics. Actually, throughout this slide, this talk, the physics understanding that we are using actually quite simple. This is one thing that I actually learned in the past years of research. Our multimodal foundation model like GPT-4o, they really have sort of human-like physical understanding capacities. We asked about basically how heavy it is. It can carry very rich common sense knowledge to give a very reasonable answer about that. It's not only about the mass, but also potentially frictions and yaw modulars and so on and so forth. It's not good at estimating absolute scales, but it's pretty good about informing basically the relative scales of different physical parameters. And also it can help us to reason to conduct dimension analysis, which is important here because it's just monocular image, right? The ball can be arbitrarily large or small. Because of that, it will influence basically how fast our video runs, right? Because our gravity is grounded by real world scale, right? So this is important, but actually turns out that the GPT-4 works pretty well. We actually published a paper about how to leverage those type of multimodal foundation model to estimate the dense physical fields, like the roughness of different surface, also like the electric conductivity or thermal conductivity of different materials and so on. That's called nerve to physics, which is also an interesting work that I didn't cover here. And in the end, we also need to understand the appearance of the background because the object will move. And the next is simple. After we figure out different rigid body object and so on, we just run dynamic simulation, like simple rigid body simulation, and it can give us different predictions of the different remote future. And then the next will just compose them, render them out, and refine them, and then give us a final video footage. For that part, it's a combination of physical-based rendering because the object has moved. So we need to get a little bit shadow and shading on that, but the composition will need to feel natural. So we get generative models to basically do the final refinement stuff. That part is a little bit ad hoc. Later on, we'll show in another work that we get more principled results for this type of rendering process. Here is some of quality results. And here is a very simple top-down view of the curling balls. And this is our results. And here is the domino cases. And finally, I think this basically reflects one of the few videos that we have shown. And here is a different object composition. As you can see here, there are some of the failure cases because that the perfect geometry understanding is really hard. So once we get flattened edges in the segmentation, we get some unrealistic conditions. Yeah, please.
I have a question. So like in all of these examples you were showing of the baselines, are they conditioned on only one frame and like text description? Because I was wondering if you gave them like multiple frames, like they get to see some of the dominoes falling or some forces applied to the ball if they could.
And then whether they are able to do interpolation based on the motion.
Yeah, because right now they're just doing like very crazy things.
That's right. That's right. So I'm actually not very well aware actually generative video predictive model that are trying to take past multiple frames and then predict, but this is definitely possible. And actually for generative models, the more that you are able to give, the better that we are able to predict.
I mean, the older methods, stochastic video prediction, work like that. It's very recent that they start only from one frame.
That's right. That's right. So for the past video generation, they are able to do that. It's not at a photorealistic level, right? Yeah, but yes, I agree with you. Those type of motion forecasting works, they are trying to do that at the image level as well. Yeah.
I guess on top of that, you could also maybe, like if you have a video clip, you could also use it to infer some of the parameters that you are using GPT for to.
That's right. That's right. I'm going to talk about interactive video in the next part. Yeah, but here is like we focus on very post set. Yeah.
Are you just simulating like some 2D projection of like the real world, like in Box 2D, just like engine, or like, and you only use this like the normals and stuff for rendering purposes?
Yes, it's also a very good question. I'm going to answer that in the next 5 slides. Okay.
So
Yes.
how's the range of the physics can you simulate? I mean, something like the clothes, the soft things, can you use the GPT to extract the property?
Yes, those are also some of the questions I'm going to answer in the 5 slides. Yes, that's a great question. Here is actually limited to rigid.
Yes. Maybe one last question. My question is,
I have a question.
reconstruct 3D from this image, like you reconstruct every object of this image.
No, this one is in-plane rotation. We don't have to reconstruct every 3D object. We need 2D geometries for collision depths. Yes. Yeah, but you need to get a model object. That means whenever you have occlusions, you also need to get the entire object. Any question online?
Yes. So great talk. I want to ask about some opinion, like people may have some argument that if we have a large enough model and enough data, this video model will ultimately get some physics. Like if you're trained maybe 2 or 3 years later, this physics, this video model will get some kind of physics. What do you think of this kind of like expectations instead of like this kind of explicit modeling?
Yeah, very great question. I want to actually touch that later from a comparison against like a specialized video generative model that trained for model specialized physical effects. But the answer is yes. So if we only care about content creation, I believe that is the future. So whenever we want to model some physical phenomena, we should really train a specialized diffusion models that are trying to mimic or trying to basically reflect the best possible physical phenomena through either tons of simulation data or tons of real world data that contains those physical phenomena. That means that in the real world, there are all kinds of different applications that we don't only need video, we also need access to the state. We want to access, for instance, in robotics, when we want to simulate the rigid body movement, we are not only just care about the video sensory observation, we also care about whether those 2 objects actually collide or not. So we need to have the full access in many situations in order to make our interactive videos and sort of word models to be useful for broader domains beyond entertainment and content creation. That is my answer why we still care about basically physical simulations here, right? And we can definitely discuss about that later, right? So for the sake of time, I might actually skip a little bit, but I really want to show some of the really nice imaginations of our diffusion-based models. And yeah, we do have some of the controllabilities, and you can get a very fine-grained control depends on different user interactions. And the diversity can come out of a range of different physical property estimations and also different user interactions. And here are some of the generative diverse samples and real-world diverse samples. I think here we just tweak the mass of the object as well as the friction of the surface between the object and also the bookshelf. And that results in different diverse samples. So if you want to play with some web demo, here is a website, and it's a real-time web demo. In order to make it real-time, we get rid of those type of generative model sort of refinement parts, so you can see the shading a little bit unrealistic. But you know, you can try to do different things. Like I can also try to replicate this type of scenarios. Right?
So do you keep the force like in actual units in Newton or the input, or
the actual unit and actual skill, but that requires a good skill or dimension analysis. And say if we have an apple, they will make our life much easier because Apple have just similar scales. For some of the cases, you can see the gravity seems a little bit too heavy, and sometimes it's too small. It's because our dimension analysis might be a little bit off. Yeah, that is one of the disadvantages of estimating everything from a molecular setting. Yeah. So as we mentioned before, right, this is 2D world plus rigid body only. Next, I'm going to show extending this idea to 3D dynamics and multi-physics, including non-rigid objects, clothes, and all those type of different sorts of soft objects and so on.
So
and
before you go into that, can you go to the whole diagram, because there were many technical.
Yeah.
There was a lot of technical content there.
Right.
So
yeah.
I mean, why starting from one image? Why don't you start from an like situation where I mean, when we study a phenomenon, we first we don't go to the most difficult situation
right
directly. You can do first, for example, 100 images, then 20 images, then 4 images, then stereo, then 1 image, right? And I can tell you, I mean, because we spent yesterday the whole day playing with Pi Zero.
Yes.
I mean, even with moving camera, and there is complete lack of 3D perception.
Yes.
And I'm wondering really, what kind of 3D can you get here unless you use like depth? Even with depth, anything, probably you cannot get the right depth to get a good simulation.
Yeah, I can tell you a little bit behind story, behind story. So we really start from this. I want my student to understand a video clip of different natural things and trying to basically interact with each other, like the curling cases, right? And in 3D. And I want to say basically now let's try to do a 4D understanding from that video, establish a dynamic 3D world, and then we are able to get more system identification like physical understanding, which can significantly reduce our uncertainty. And by that time, it's quite amazing that it's quite surprising to me that our 4D modeling or understanding is not sufficient enough for us to conduct such a task to do perception. So one thing is our image level motion tracking is fine, but our 3D coherent motion tracking at that time is not good enough. And now we have many different tools. This also actually inspires some of my group's own work in terms towards better generic 4D understanding. Now we have some of the other works like Monster or Andrew Kanazawa's lab has some of the works on 4D modeling. I think it's the right time for us actually to touch better about simultaneously model geometry and the motion from the 4D world through just one.
But tell me here actually, how do you go in this arrow from the perception to the full 3D world which you use in
I'm going
in an engine?
Yeah, I'm going to answer that in our next work. Yes. So now let's talk about the 3D dynamics. All right. So as we can see, right? So that requires a full 3D understanding of the world. And that is actually also quite challenging. It's still coming from a single image, just like Costa said. This is highly opposed compared against if we have video observations. So we start from there as a natural extension because we have seen so many nice progresses in our field across different multiple fundamental blocks. I'm going to explain one by one. Firstly, we need to get instance segmentation. We also need to get a full geometry of the scene, including the complete object geometry, as well as the background geometry. We also need to, from any perspective image, we need to understand the direction of the gravity. In previous cases, it's simple because it's mostly like a 2D-ish world that estimating the vertical direction is easy, right? And in the meantime, we also need to model the appearance of the object and also, again, reason the background. And once we are able to get the 3D mesh, we also need to make sure that they are perfectly aligned with the image. And in the end, we also want to estimate lighting conditions because as you can see, it will cast shadows and so on and so forth. So to answer Costa's questions, I think we have a lot of amazing tools here. So we use segmented anything, we use Duster, and for grounding plane, we use neural vanishing point. And for texture mesh, we use a generative texture mesh. As you can see, a lot of engineering work that happens here with my student. And we use SD XL to basically do imprinting. And we establish latest greatest like point-based matching and then using PMP to align these 3 mesh back into the image to make sure that alignment is really nice. And we estimate lighting condition using diffusion light. So all of those happens, I think, are the tools that published within like 3 years. So without those toolkits, we cannot really get a pretty comprehensive understanding of the world. That being said, still, as what Costa said, we cannot arbitrarily take an image and then we are able to get a complete 3D understanding. As we can see here, we basically focus on our work, we call it miniature world. I don't want to overclaim. At this moment, we focus on object-centric things because that will make our life much easier. And after we conduct all those type of fundamental perceptions, and we are able to get a pretty complete world, allow us to do 3D dynamic simulation. And here the challenge lies in how can we actually simulate multiple physics effects, including rigid body effects and non-rigid body effects. If you have play with physical simulation, this is actually a hard part. So how can we actually make 2 basic physical simulators working together? So also thanks to the advances, actually one of the key advances here actually happens at PIM before. It's called moving least square material point as method. It developed by Fan Fu before when he was at Penn. And we actually leverage that. That allow us to model both rigid body physics and elastic and plastic physics, which is really nice tools that we can get. And finally, we use physical-based renderings to actually cast the shadows here, compose them all together using alpha blending and get the final video footage.
Do you assume the ground plane and gravity vector are aligned?
Sorry, what?
Do you assume like the gravity vector is aligned with the ground plane?
Yes, that is one of the assumptions.
It's kind of like a nitpicky, like I think in most cases it will work.
Yeah, there are some of the corner cases.
Yeah.
Any other questions?
No, that's perfect. I mean, it's good to emphasize that without computer vision, it cannot be solved. So, there are 10 important papers there from computer vision that enable that.
Yes, this is not like our single effort. This is like a community effort in order to achieve these results. We are just compose them together and build a system. Yes.
Can you comment on like how much manual prompting or tuning I have to do for like those 10 different tools you shared earlier?
This is something that I specifically ask my student, do not tune hyperparameters in the validation video footage. So all our user study video footage, we don't tune any hyperparameter.
So I was asking about like all of the pre-processing, you have like.
Yeah,
like,
yeah.
so all of those
On the training during development, they need to train a lot in order to make sure that these things are comparable, with our downstream physical simulation. Because in the end, if you get some metrics that looks better from those type of different task specific metrics, it's not necessarily transferred to be you are able to get a better simulation.
Yeah, I just find it hard to believe because like for some tasks, I can imagine like for a very specific scene, I would need to tune like, I don't know, the ground plane detector like this way to make it match this scene.
Yeah.
Yeah, so like,
This is a nice thing that I think is a success of large vision models. So as you can see, one of the common cases for here is most of those models, they trained on multiple different data sets. They have generalization capacities. This is different from 5 years ago when we work on CVPR. We get better numbers on one data set. Those models now started to get generalizable. I'm actually quite surprised with some of the models, like especially like instance mesh or Duster 3R. They actually works really well in many situations. Of course, there will be corner cases. This is why we focus on object-centric things. But this is the real progress that happens in CVPR community today.
yeah. I guess just one more follow-up. So if you go to the next slide.
Yeah.
So what's it like, what if I just took all like 10 of those inputs, I view them all as like a different channel or modality, and then I just train a neural network to predict like the next time steps, like all 10 of those modalities? Is that right? Do you think, like, what do you think about that approach?
That's a very excellent question. This is something that we are also looking to, and I know that some other groups are looking to. The way that I think you think about that is for those two different components, right? So we can definitely build a diffusion model, especially for the last one. If we have all those type of information, getting potential diffusion model is no problem. Right? And the way is how you actually, which part that you want to use grounded knowledge, or which part that you want the model to have. This is actually a design choice that we need to be very cautious based on what we do. All right, so for the sake of time, I might just need to skip some of the works, but here is some of the different 3D interactions, and we also compare. Those are the almost like latest greatest model by the end of the year. And as you can see, like for clean AI, actually, we give privileged information. Clean AI can take user input. User can plot a trajectory. We actually provide them a motion trajectory of the future and just see how well the dynamics works. It turned to underestimate the gravity, and it have the actual floating in the air effects. And we are also able to do material editing, and assuming this object have a different materials and multiple different objects interact with each other and so on and so forth. And of course, we can do very precise control, like switch different materials, like elastic and rigid, soft and soft, and we can control different directions in 3D because now we have full 3D, and we can move the chair away, and the Snorlax will fall on the ground. And the failures, yeah. This type of pipeline, as you can see, heavily rely on our perception model. Any one of those type of perception model failures might result in quite obvious artifacts that in our rendering. Here is one of the cases where our lighting estimation is wrong. So we cannot even replicate the original image, and when the object is on the ground, a casted shadow is not really correct. And here we can see different rendering effects because our estimate albedo actually bakes on the shadows in its albedo estimation. And here, as we can see, that we underestimate the rigidity of this part. We thought this is like a cloth-like material. So as you can see, the simulation is actually not correct. So this is one of the challenge, for generative models. When it feels in a holistic way. It feels in the sense that it still looks like legit videos, right? This Snorlax like flying in the air and slowly fall on the ground. When it feels that people can really have a very sharp eye to identify this part is actually not natural. This is something that we need to resolve for future for model-based simulation. Okay, so now what can we do for interactive with videos instead of interactive with images? So what video offers is obviously like what you guys mentioned, more observations. That means potentially we can get more complete scene models, and we might observe some of the dynamics already. And of course, we have higher expectation on videos because we have more, observations, right? We need them to be more temporal coherent with existing dynamics, and we need richer capacities and more complex interactions. So what I mean more complex interactions, here I show some of the videos. Given one of the image here, I want to simulate very comprehensive dynamic weather effects, like what if the scene gets flooded, what if there's smoke, and there will be snows, and so on and so forth. Those added physical entity not only need to interact with the scene very well, but also our rendering need to be seamlessly composed together with the existing scene to show a convincing rendering. I'm not going to those details. This is like a work that has been done roughly like 2.5 years ago. And here are some of the results that we can see. And from another part that we also want to, interact with the scene by changing its lighting conditions. And here is two videos that show captured in the day, and we are able to turn it into the dark, and then getting a convincing interactions between like the different lighting conditions and so on with the scene models. All of them requires a complete understanding of the 3D scenes, thanks to the fact that we have more observations and we can get more complete, but also in the meantime need to understand the lighting physics here. All right. So far that we discussed about specialized interactions, like we have a specialized lighting physics model, weather physics model, or dynamic physics model, and so on. So now what if I want to ask, can I actually go something crazy? Like I throw a basketball with fire towards a vase with flowers and then break the vase into different collisions. As you can see, right? If I want to give a talk, like 3 days before my talk, I want to ask my student, hey, can you actually do this type of simulation to me? Actually, it's not really easy. Right? Someone need to do some very heavy lifting in order to make this thing to happen. We don't want our student to work on a specific demo by writing so much different complicated, code. Can we actually, the very natural question is, can we unify simulations and then build a language instruction, just like any other video generated models, right? And then to build a VFX tool that actually works for everyone instead of only just VFX experts. So here is what we are able to get, fully automatic, given this language as the input, and we are able to get this type of results. So this has been just recently accepted by 3DV and will be presented later. So given our input video and input instruction, here we will do the similar stuff. We'll based on this video to get a complete holistic scene models with geometry, semantics, appearance, and lighting, and so on. The different part lies in the fact that we have some atomic functions, different simulation component, like rendering is like the different composition functions and PBR functions, and physical simulation is just particle simulations and fractures and so on. And animation is essentially we want to set a trajectories and so on and so forth. Now, we are able to actually leverage those large foundation models to arrange those type of different functions together so that we are able to convert this instruction into a readable code. So it's quite surprising that it works pretty well. Everything is fully generated, and we take by providing some of the prompt. This is like in context learning. We do not really do some fine tuning and so on and so forth. We provide roughly 20 examples to large foundation models. It learns how to compose them together, right? We first model the video, and then we retrieve the basketball, and we localize where the vase is, and we set a trajectory between the basketball and the vase. We add fire onto the basketball, and we simulate, and then later on we render it out. And that gave us the final videos. And for the sake of time, I'm going to skip some of it, but we are able to change the materials, drop 5 basketballs, and insert some animated figures here, and so on and so forth. And it understands the scene, it can interact with the geometry of the scene, and even indoors and outdoors, it can simulate some of the weird situations. And yeah, it cannot find a Tesla Cybertruck from our assets back, by the way. Yeah. And we do have some comparisons against different diffusion models, like especially like we also compare against like Pika 1.5. Pika understands basketball, and Pika does not count correctly, and it might not really get us a very nice physics. But as you can see, the rendering effects is really good. I feel that nowadays those generative models are really good at replacing physical-based renderings. In order to tweaking those type of realistic lighting physics and so on, our students work on that with Blender for a really long time, but Pika simply just knew it. And here is what I'm going to show. Here is those Pika effects like melting. It's a specific diffusion model that trying to train and fine-tune on just one physical effects. Let's see what they are able to get. Here is Pika's effect, here is our effects. As you can see, they have some advantage in terms of it looks more realistic. And it gets a lot of different accessories like the dirt and so on. But the physics is not correct, right? A lot of fractures pass through the table and get into the ground. How we are able to combine the best of these two worlds is still a remaining.
That's really quick. All the objects that you're like inserting into the scene, they're just like pre-existing assets that the LLM is just like pulling.
Yes, but it's a huge asset coming from object first.
Okay.
So it covers all of things.
Okay. Yes.
So yeah, I only have like 10 minutes left. I will quickly go over how can we actually go even beyond to get an interactive world. The input is just a single video, but the output is actually a game that everyone can play. And why we want to do that? The reason is everything here you can see from this screenshot of the game, it comes with a price tag. In total, it's around, 200K, roughly 2 PhDs annual cost, right, for PI, right? We don't really want you guys to spend, 2 years on just creating such a screenshot. We want smart ways to getting this done. So the smart way is actually allowing everyone to just take a video and then convert that into a game-ready assets. The general idea is the same there. So we want to reason the geometry, composition of the object, and appearance based on nerve. And then we want to convert them into basically interactive 3D assets, and then compose them together with a physical engine. And that allows us to do something that we convert. If you are familiar with self-driving data sets, you know that this comes from Kitty data set. We actually convert the Kitty data set into just a temple run style game. And we actually collect coins and you are able to win this game. And we also convert that into a GTA style game. Note that all the cars in the original Kitty, they can be collided. We are able to run into those cars and then get a real world cliche. All right, yeah. And here is a famous garden verse coming from the nerve. I really want to hit that the base, and now we are able to do that. And of course, they have some real world practices, and we are able to build a robot simulator for everyone's home. And the web game asset is also ready here. You can scan the QR code and then play that. Now, the last part of my talk, I want to just cover a little bit about our latest works that towards this interactive environment. And here is my student, the guy who did the video to game. We want to convert this. This is a UI you see, my lab's printing office, and it's a kitchen and plus printers. So this is how we collect the data. It's just a static data, no interactions whatsoever, right? And then, of course, we are able to convert that into a null view renderings. And this is basically it's rendered views, and we can move our camera freely. But in order to actually get in these entire interactions of the environment, what are the things that you want to do? Microwave, yes. Any other stuff? Yes.
Water tank.
Water tank. Any other stuff?
Closet.
Sorry, what? The closet. Yes, you can see a lot of different like doors and fridges. We want to open them, right? And like what you said, the water tank coming in future. We want to actually fill in the water tank with a lot of water. So next project. Here, I want to showcase that Now we are able to open the different doors and the fridge doors and so on and so forth. So well, from this passive collection of the static videos. And that is our next project that for interactive scenes with full articulation. It's a work that done by a different team, of course, different locations. So for the sake of time, I will briefly go over this different part. In order to render well, we need and also simulate well, we need dual representations. The reason is SDF is really good at capture geometry that enables physical interactions, but it cannot render well. So we need Gaussians on top of those SDF. It's a combined representation that really nailed in basically both simulation and rendering. And the next part is important. We need articulation reasonings. That means we want to segment out different, articulated objects like doors and drawers, doors of drawers and cabinets. And we also need to reason its 3D articulation axis and also the joint type, like whether it's a revolve joint or prismatic joint. And when after we finish that, in order to make it interactable, we only observe its facade, right? We need to get the interior to be complete. And that part, we are able to leverage generative models, trying to complete a geometry and follow some of the experiences and also using its exterior textures, trying to, capturing the hidden regions and then getting a realistic feelings. And afterwards, we get interactable digital twins that allow us to open the drawers, open cabinets, and having different moving objects similar as the video to game ones, and also conduct novel video synthesis. And here are some different experiments we can see. And you already noticed, in order to get those interactability, we trade off a little bit about rendering fidelity. It's slightly worse than standard 3D Gaussian GS. It's like roughly 2 dB worse in terms of PSN. Yeah. And we also compare against like existing articulation outstanding work from David Fohey's group, and also some of the sort of articulation outstanding, same level articulation outstanding from existing work. So you can see that is URDF former from UW and the digital cousin from Stanford. Most of those existing works, they are based on retrieval-based methods. That means when we understand, oh, there is a cabinet, let's retrieve a similar cabinet, and then let's compose them. So it's not really digital twin. So this is why Stanford, they're really good at naming. They call it digital cousin, which is a really good name, by the way. But we are able to reflect the reality as you can see. I'm going to skip this, and we are able to build the first shooter game. And importantly, when we build these digital twins, given the fact that it has interactive abilities, so we are able to just train a policy in this simulation, just in specific this environment, and then we are able to deploy it. Think about the future. When we want to deploy a household robots to our home, we can just ask the users to just take a video record of their home. And then before we deliver that robot into our home, the robot already have been trained, repetitively trained on that digital twin environment for a while. They know our home very well. Then from day one, they are able to be able to behave nicely in our environment. And that is our final. All right, so that's basically conclude my talk. Here is just a summary of different projects if you are interested to know more about different part of my work, our group's work. And the next, there are just a few remaining open questions, right? To give a quick summary, we want to get interactive images and videos and physical. Our approach is we want to synergize 3D perception, physical simulation, and rendering. But there are a few questions that I didn't manage to answer at this moment, right? One is error propagation. Right? This is a pipeline system. Any part, if there are some errors, will reflect it into the videos. So we see some of the artifacts in from our failure cases. So is there anything that we are able to do better? And the second is, can we actually better bridge the best of the world of model-based simulation and the data-driven generation? As you can see, at this moment, most of the methods are pretty heavy on the both either one of the side of the axis. And the conditional video generation or my group's work, we use some of the generative approach, but it's very small part. Most of the part is on the model-based simulation side, right? whether there's some really nice someplace in between that can leverage the best of the two. So we have looked into either generative modeling as a post-processing, or we train simulation for creating new data for generative models. But those, I think, are just temporary solutions. In the end, we need some more physically informed generative models, right? And the third one, actually, we also discussed, we are able to model the world to enable interaction. But if we have the capacity to interact with the world a little bit, like if I just lift it or poke it a little bit and then observe the consequence, we probably were able to get better modeling of the world, to get a better digital twins, right? So the last one I think is also important. We build the world models or world simulators. It's not only for just creating a VFX effects or just creating games, or at this moment we have been using them for global simulation. I do think our community need to think a little bit more to broaden its impact about what if we are able to have a really nice tool to bridge the reality and the digital world, because different domains, their own problems, they basically just understand how world works in some other different perspectives. They have their model-based knowledge, and many cases, they are able to formalize those knowledge. Can we actually bridge this gap? But the only gap that they have is actually they cannot really have access to the reality very easily. And I think computer vision have the capacity of doing that. I've been collaborating with crop scientists on building digital twins for agriculture and then make smart decision making in agriculture. But this is just one example. I do see a lot of nice, potential opportunities there. And for that, I will basically just thank my collaborators and funding agencies. I'm happy to take a little bit more questions if time. Thank you.
Question about the dual SDF Gaussian representation in the last work. I'm just curious about like the algorithmic flow. Like, do you start with like the segmentation to get like the rigid bodies, and then like you train like a Gaussian splatting like model, and then you associate those Gaussians as like some density sample point cloud to train the SDF?
Yeah, I think for that work, our first citizen geometry. Firstly, get a complete geometry, I guess from News2, but whether it's News2 or some other newer SDF method, but I will get some complete geometry. We segment over the geometry, and then we attach Gaussians on those geometry, and we complete the geometry of that object based on generative model. So essentially, the first citizen is geometry, surface geometry, because later on we will use that for physics. Gaussians are attached on the to enable that. That is our strategy, but it's not. Potentially there will be some methods, right? That are trying to establish a dual representation that do not conflict with each other. The challenge of training separate ones is you'll fight against each other. There are some parts that we want to render well. There are some Gaussians, but in the SDF geometry that does not exist this one, right? Simulation and rendering, they will fight against each other.
Yeah, I wonder if there's like some simple constraints that can help like make them more coherent. Like, for example, like the Gaussian should line like the zero level set of the SDF, and like the gradient of the SDF should align with like the orientation of the Gaussian.
This is actually what we did, but you can see that there is a trade-off. When you sacrifice the flexibility of your Gaussians, basically you sacrifice a little bit on the rendering adaptive.
Thanks.
Yes.
First of all, in the work example with like a model video generation and with some very subtle model like the Kelly. That's the problem when camera pose is changing. Like for example, when we are human shooting the videos, we're actually not just stably stick there, but we are actually trying to move it around.
Yes.
But the current generation model seems to fail to understand what's going on with this moving around. And if you try to train it, it will take like a very large distribution shift, because you cannot even do this correctly in fixed pose. But if the camera pose is moving, then the training data will scale a lot much than before. Like, how do you think we can solve this problem, like the camera pose moving?
You mean the generative models?
Yeah, for video generation.
I'm not an expert there, but I'm aware there are quite a few words that started to disentangle the camera dynamics and also the sim methods.
Yeah.
Now it is possible that we can precisely control one of them. rather than, but for generative models, whether they understand the camera motion very well, like structure for motion do, I'm not 100% sure. Yeah, and probably it could be the case that you might actually face the problem that you are mentioning at this point. But for generation purposes, nowadays they are able to perfectly distinguish those two cases.
Currently, let's follow up on these questions. Currently, it seems that most of works are still struggling to modeling the one object movement. But for manipulation, we think we like one like the robots can modeling many objects.
Yes, it's even more difficult.
Like
Yes.
very complex things.
Yes.
How long do you think it takes? Like how many years to have some kind of model that can do like 3 objects interacting physically correct?
Okay. I'm very bad at prediction because if I predict things 3 years ago, I cannot predict anything here.
True.
So I don't want to be over optimistic, but I think for many situations, if you just care about looking good, I think it just, you just need to feed a little bit more data. So I talk with some of my friends that has hands-on experience working on clean models and working on some other sort of video generative models. They believe it's a matter of. Yeah, although I respectfully disagree that it's only data problem. But for your robot simulation cases, I think we need access to state. Unless you just want to do NPCs, but if you want to do sim to real transfer, that means you need to get a state to describe the reward functions and so on and so forth. Having a grounded physics there will be still helpful.
Maybe I have one question. Thank you for the inspiring talk. So I think this is like cool work. I think your work also follows the flow of perception, simulation, and rendering.
Yeah.
So currently, if you look at the result, you may still think there is a gap between the real world like synthesis. So how do you think which one is the bottleneck we should look into? Like you are currently not satisfied with the result from the component.
Yeah, what I learned from those works is we still need to advance a bit on, we discussed before, 40-word model. I think it's quite surprising to me that given arbitrary videos that we still haven't been able to get a very complete and comprehensive and coherent 4D understanding of that. It's advancing there, but it's not there yet. Another one is physical understanding. And physics simulation are there. So we do have quite a few physics simulation that we can use. The only thing is they have very strong assumption about you need a very clean geometry and you need very precise physics that we cannot offer at this moment if we just reason from the videos. Bridging this gap could potentially making things to work better. From rendering side, and before I have a very strong preference on physical-based rendering, but at this moment, from time to time, I do think generative model and conditional generative model can do a lot of amazing things. And the rendering side, I don't really worry too much. I'm not discouraging you guys working on immersive graphics. It's still a very important problem, but from time to time, I think the diffusion models can do those heavy liftings. The key lies in the physics side. And one interesting one is how can we actually make our generative model to be better grounded with academic resource instead of just generating unlimited about simulation data and then trying to feed them into generative models. It's not efficient, and also there still exists a gap, right? So is there any smarter way that we can make a smarter diffusion model that directly reflect the world dynamics? That would be something I think is interesting. I think it's not really impossible. It's definitely.
Yeah.
Yes.
I mean, it's a wonderful talk, Shenlong. You said if you want visually appealing,
yes,
you need more data. But then I go to the roboticists, and then they say, "Oh, also we're going to solve the problem of data. We don't need all this physics engine."
Yeah, for robotics, I would argue it's a different story. So it really depends on whether you believe that robotics need interactive data or not. If it's not interactive data, if the robot just need to watch videos and then they already know everything, then I believe that is a case. But I believe that in order to make robotics happen, we need interactive data. Whenever we need interactive data, the real world pace is a bottleneck. So we can only operate our robot in such a pace. People try to scale up by building a robot factory. It has been proven to be a failure example, right? Now people started to look into, using simulation, because in one GPU you can simulate 10,000 different words and simultaneously train a robot policy. Basically, it's like a simulation over a time machine. And same argument happens when we do the digital twin for agriculture. Say, digital twin is really a time machine for the year, because if we think about agriculture life cycle, we're in the middle of cornfield and the soybean field, and our soybean life cycle is like roughly like 180 days or something like that. And in order to make any decisions, you have to see half a year to see the consequence. But using simulation, you're able to do multiple different trials in your computer in one day. And that is a huge advantage. So in my opinion, that is a core value of still building a world simulator. Any decision making that requires an interactive environment, right? We are able to solve it better. Yes.
As for the physically plausible video generation, you have mentioned that large language model is good at infer the physical properties. And in this case, if we give them an initial state, for example, the force and the physical properties estimated by the language model, maybe the language model can calculate what might be the position of the next data. If we condition on this to generate the few frames of the future, and we repeatedly do this autoregressively, do you think this language model plus the video generation will generate physically plausible videos?
It depends on what you mean by language model will predict. If you just use next token prediction to do this type of calculation, I doubt the language model will give you very precise results. If you are referring to a language model as an agent, trying to write a piece of code to write a rigid body simulation and then run it, yes, that is exactly. So it really depends. Next token prediction to do very comprehensive computation, like a numerical computation, at this moment is still. Any other questions?
I'm just wondering, like, in all your examples, you're just doing like open loop simulation. Like you fit some model and then you do open loop predictions. But I'm wondering, like, especially once you get into robotics and the robot can autonomously collect data and then like you can refine your model parameters, like, are you thinking about closing the loop?
Yes, we are trying to work on it. This is definitely something that will be added to our groups next. But I do think this is the open problem now to that. Once we have more interactions, we can definitely significantly reduce the uncertainty of our physical world.
Thanks.
All right, thank you.
And then we talk.